minus, okay. All right, so we're in section 3.8 today. What was our last section? We're in chapter 3. We'll jump from chapter 3 to chapter 5 after this. All right, so Newton's method is a method to approximate the zeros of a function. So I have some function, not a nice function. We can't factor it, all these other techniques that we normally use. But we want to find the zeros. Finding zeros is an important process. So that's what we're interested in today. And when I say find, we're going to approximate. We're going to do some approximation. All right. Interestingly, when Newton came up with Newton's method, and sometimes you'll see it called the Newton-Raphson method, he didn't think about it the way that we present it. He didn't think about it in terms of its relationship to calculus, really. It wasn't until later that this method was kind of, the relationship was made. And Newton only used Newton's method for polynomials. And what Newton did was generate a sequence of polynomials that approximated this other function. So he kind of did it a different way than we do the method that we named after him. All right, so our preliminaries. We have a function f. And it's continuous. It's a nice function. And we have some interval. It's continuous on this interval. And we know it's differentiable. We can take derivatives. On the open interval. So we have to be able to take derivatives. If we have some function where we have a problem with the derivative somewhere in the interval, Newton's method, we could have a problem with Newton's method. And we know there's a zero somewhere in this interval. So that's what we need to know that we need to start with a guess. So we need to know there's a zero somewhere in there. So before we start, what if we have some kind of function, and Newton's method, we would usually, it's going to be like programmed into a calculator or into a computer. If we didn't have a guess, if we didn't know where a zero was of a function, and we're not just using we're not using our calculator because we're going to be kind of calculating these out by hand, how would we decide if a function had a zero on an interval? Without graphing and looking at the graph, yeah. Oh, yeah. Okay, well, yeah, if somewhere we know it's less than zero here and greater than zero here, somewhere between those two values, it has to have a zero. What would be another way we could guess that it might have a zero somewhere? What if we just plugged in an x value and it was pretty close to zero? Or we say, oh, when x is 2, the function evaluates to 0.5. That's pretty close to zero. So you can say, oh, we're close to zero, so I'm going to guess that's close to zero. So there are some ways that we can figure out somewhere in a range between some numbers or close to this number, we have a zero, even if we can't graph it and look at the graph. All right. So let me draw a picture that illustrates what we're doing with Newton's method. Visually, it's pretty easy. It's pretty easy to understand. So there's my y and my x, and I have some function that's doing something like this. And we're in this interval from a to b. So we know that there's a zero somewhere, and I'm going to call the zero c. So somehow or the other, we approximate, we say the 0 is approximately, and I'm just going to put this here because it's easier to draw my picture. At x equals x1. So the coordinate of this point is x1 comma f of x1. And what we're going to do is we're going to approximate the function at x1, at that point x1 f of x1, with its tangent line. Because a tangent line is at a particular point, we know is a linear approximation of the function. So I'm going to draw a tangent line like so, and we're going to say, and I know this isn't a perfect tangent line, we're going to say the 0 of the tangent line is approximately the 0 of the function, because the tangent line approximates the function at that point. And I'm going to call that point x2. I'm going to say x2 is approximately the 0 of f. The tangent line approximates the function, so the 0 of the tangent line is approximately the 0 of the function. And then what we're going to do is say, well, let's let x2, f of x2, let's find the tangent line there. And approximate the 0 of the function. I know this is not a perfect tangent line, but we get the idea. And then x3 is going to be approximately the 0 of the function, because the red tangent line approximates the function a little closer to the actual 0. So the 0 of that tangent line should be a little closer to the 0 of the function. So then we're going to say x3 is the new approximation. And then we continue this for as long as we need to get closer. So we would come up here and say x3, f of x3, find the intercept of that tangent line, go down here, and keep going until we get as close as we want to get to our 0. Now Newton's method is really nice. We'll talk about that a little more later. It actually converges when we're close to a 0. It converges extremely rapidly, and that's why it's so useful. All right, so everybody good with the idea of Newton's method? So there's a nice picture of how we're going to apply it. Now let's talk about how we're going to calculate. So let's calculate x2. So we have a guess. Our initial guess is x1. So I'm going to say using guess of x1. The slope of the tangent line at x1 is what? Well, how do we find the slope of the tangent line? Derivative. It's going to be f prime at x1. There's our slope. And we have the points. The line goes through. Oops. x1, f of x1. And we want to find the intercept of that tangent line, x2 comma 0. We want to find the intercept, the x-intercept of that tangent line. Well, we have a slope. We have a point. We can write the equation of that line. And I'm going to write it initially using this point, and we'll make it go through. Then we're going to solve for x2 using this point. So I'm going to say y minus f of x1 equals f prime of x1 times x minus x1 using point slope form. And then I'm just going to isolate y here, so let me rewrite this. I'm going to say y equals f prime x1, x minus x1, plus f of x1. Now we're going to substitute at x2 comma 0, 0 equals f prime of x1, x2 minus x1 plus f of x1. And we solve for x2. So I'm going to do this all in one step. Solving for x2, we want our new approximation, and we'll get x2 just in terms of our initial guess and the function at our initial guess and the derivative. So x2, finally, equals x1 minus f of x1 over f prime of x1. And this is our new approximation. And then what we would do from here is we're going to iterate this process for our new approximations. So we're going to say x2 is our new approximation. So x3 is x2 minus f of x2 over f prime of x2. So I'm going to say iterate new and hopefully better, usually better, approximations. So that is, i.e., x3 equals x2, which we solve for here, minus f of x2, whoops, over f prime of x2. x4 would be x3, so we just keep plugging our new numbers into the algorithm, churning it out. This is why computers are so good at this, because they're good at that kind of thing. And we're just going to repeat this step, these steps, until we get the desired accuracy. And usually for the kind of problems we'll do, the accuracy will be specified. So continue until successive iterations differ by less than 1/100th or 1/1000th, something like that. And usually that goes pretty quickly. If you have a good guess, that goes pretty quickly. And I'm going to say repeat. I'm going to say satisfied. Satisfied with the accuracy. That's what I mean there. Or your accuracy satisfies some condition. Now, if you make your initial guess x1, if that's quite a ways from a 0, it might take quite a few iterations to get close. But if you're pretty close to your 0, it should happen pretty quickly. So you can show, and it takes a little more math than we know, that if the sequence of these x1, x2, x3 converges, has some limit, then that limit must be a 0 of the function. So if the sequence of x's converges, it converges to a 0 of the function. And generally, you get double the number of decimal places of accuracy for each iteration. So that's pretty fast convergence. So if you're close to a 0, you do one more iteration, you get 2 decimal places more in accuracy. So that's another reason Newton's method is so useful, is that it converges. One, it converges to a 0. If it converges to a 0. It doesn't converge to some extraneous number. And 2, you double your accuracy with each iteration. So it converges pretty quickly. When would Newton's method fail? Just looking at our iteration formula. Yeah. If we end up with f prime equals 0 somewhere in that interval, so Newton's method would fail. So you'd get a undefined quantity there. Sometimes you can get around that by picking it. That might mean you picked a bad value for your initial guess. You might have picked a bad. You might have picked something near a maximum or a minimum to get a f prime equals 0. So you can change your initial guess and get around that. Sometimes the function just isn't nice and Newton's method doesn't work. All right, so I just want to look at one example because it's pretty easy to apply this. It's tedious, but pretty easy. What I would ask is when we use Newton's method, I want you to tell me how you came up with your initial guess. Not I graphed it and looked at it in the calculator, but some other analytical method. If you program this into your calculator, or you have a sequence of buttons that you can push to get new approximations, what I would ask is you don't necessarily have to write each of these out, but I would ask that you show the quantity that you get at each step. So x1 equals this, x2 equals this, x3 equals this. So on a quiz or a test, then I can see, okay, if your numbers start going crazy, I can tell that there's some kind of problem with your Newton's method. But you do want to, if you want to, you can automate this to an extent. I don't ask you to write out every fraction of your calculation. All right, so let's look at a quick example. If we should have time, I'll talk about a real valued function where something interesting happens with Newton's method. And then on Thursday, after we talk about hyperbolic functions, or before we talk about hyperbolic functions, I'll talk about what happens with Newton's method with complex functions, which is pretty interesting. All right, so questions before we do our example. Okay. So let's say we have f of x equals x to the third minus 2x minus 5 equals 0. So we want to approximate. Approximate the root with 3 iterations of Newton's method. So this problem specifies how many iterations. If we weren't using Newton's method for this polynomial, how would we, with the tools that we have, the algebraic tools, how would we have to go about trying to find the zeros of that polynomial? We could see if it factored, maybe. Do we remember all the way back to, what's that? Well, it's a cubic, so that add a square. Yeah, do some kind of algebraic manipulation to it to try to make it factor. That's so thinking all the way back to pre-calc. Remember the p's and the q's. and synthetic division to test our possible rational roots. Remember that whole process?
We could also try to use other graphing techniques to make graphing functions.
Other graphing techniques. So previously we would look at the factors of the last term and the factors of the leading coefficient, make our P's and Q's. So this one it would be relatively easy to test because our possible rational roots are just plus or minus 5 because our leading coefficient is 1. We could plug those in and see if we get a 0. I'm pretty sure we don't. And if we don't end up with rational roots, then we're kind of stuck. So that would be a reason that we would use Newton's method. All right, so what would be, now things get interesting when your functions have multiple zeros. And that can happen. All right, so what would be a good guess for our starting guess for this function? 2? What and why 2? So to find f of 2 is -1. What's f of 3? 16. F of 3 is 16. So f of 2 is a pretty good guess. F of 1, I'm just going to go back 1. F of 1 is -6. So this looks like, I would say that's our candidate. So we need our derivative. Newton's method gets interesting when the derivatives get messy. And that's why computers are good at this kind of thing, because you can tell it what the derivative is. Yeah, amazing. So I'm going to write the general term for our iteration. So the way you'll often see this written is x of n plus 1 equals x sub n minus f of x sub n. So x sub n cubed minus 2x sub n minus 5 over the derivative 3x sub n squared minus 2. Often you will see Newton's method written like this for a particular function. So the next term comes from plugging the previous term into this thing. So I'm going to write out, I calculated this out longhand for this one. So let me just show you my calculations. I won't ask you to do this. And if you want to think that I did these calculations in my head, that would be fine. This was easy to do in my head. Substitute it in. That equals about 2.1. And then I do x sub 3 equals, now I'm going to plug 2.1 in here. 2.1 minus 2.1 cubed minus 2 times 2.1. I'm just writing this out to show you what it looks like. Over 3 times 2.1 squared minus 2. And that's about equal to 2.0946. I'm not going to write out the next one, but we would see that x of 4, if we do one more approximation with this 2.0946 plugged in here, we would get that x of 4 is about 2.0946 also. So this would be our approximate 0 of that function. Yeah?
So if it says go to the third iteration, go to x of 4?
Yeah. Because our guess is the x of 1. And I just didn't write out this would be, what it came up with this would be 2.0946. It plugged in all those parentheses. All right. Everybody see the method? Okay. So the homework is asking you that you do some calculations. There's some functions where it asks you what goes wrong with Newton's method, or why would Newton's method go wrong, just thinking about the technique. I had a former student come and talk to me last year who's studying applied math, and we were talking about Newton's method, and he said, yeah, Mr. Beamer, we use Newton's method all the time. I never thought it would be that important. So that's another reason to see it again, is because it is, if you do any kind of applied math, Newton's method is extremely important. Okay, let me look at one example, and we're not necessarily gonna work through this one, but I want us to think about this one. Let's say we want to use Newton's method to find the zeros of this function. Anybody anybody see what might happen, what's going to happen with this one? So what does a graph of this function look like? Yeah, almost kind of like an inverse tangent, sort of. Yeah, like an S. So something like that, more or less. What's going to happen with Newton's method? It's going to keep getting further away, right? If we approximate the zero here, our tangent line is going to go out here, and then we go here, and then our tangent line is going to go out here, and then we go here, and our tangent line is going to go out here, and we just get further and further and further away. What's the problem with this function?
If the derivative is like in the has a negative exponent, then it like multiplies the
Right.
instead of divides it.
Right, it's going to end up multiplying instead of dividing it. Our approximations are going to get larger. And what's going on at the zero here? We have a vertical tangent at the zero. So this one, Newton's method would fail. We wouldn't be able to use Newton's method on this one. So that one's, that one good. It would get, you would get worse approximations with very much worse approximations with each iteration. So Newton's method fails. So I'm going to write this. Newton fails. Just for fun. All right, let me talk really quickly about a real valued function where we end up with something very interesting with Newton's method. And we'll go further with this next time. You don't have to write this down, and I'm not. This definitely wouldn't be something I would test you on. I just like to point out, to me, Newton's method is interesting. The algorithmic part is interesting. I'm more fascinated with other, like, more abstract kind of math, and that's what's interesting about this to me. All right, so let me try to draw a decent picture of this graph. It's kind of a strange one. This is supposed to be symmetrical. That one started off okay. No, that was bad. Okay, that's a little better. It's supposed to be symmetrical. This is y equals 4x to the fourth minus 4x squared. So not a particularly complicated function. And I'm going to call this root A. This root B. And this root C. And I'm going to put some points in here. And these, I know these are not going to be exactly labeled. So this is minus square root of 21 over 7. And this is negative square root of 2 over 2. And then these are the same, but positive. Square root of 21 over 7 and square root of 2 over 2. All right. In infinitely many subintervals between these 2 points, you can subdivide that interval into smaller intervals. Newton's method will lead to root A, alternating with approximations that lead to root B. Between these 2 infinitely many subintervals, we can divide it up as tiny as we want, will converge to root B or root C. At the boundaries of the interval, the method doesn't converge. Now, if we get larger than square root of 2 over 2, we converge to root C, and less than negative square root of 2 over 2, we converge to root A. Well, what's interesting is in here, we can move the tiniest amount one direction, and we converge to a different root. We can move even tinier, and we'll converge to a different root. We can subdivide that again and move even tinier and converge to a different root. So that's the definition of chaos, is that a small change in your initial conditions, your initial guess, leads to a large change in the outcome. And you can't say, well, for this amount of change, it's going to go here, because in between any 2 numbers, you get an infinite number of other points that converge to either of those other 2 points. So this is what we call chaos, and it arises in a relatively simple function using Newton's method. So that's a kind of an introduction to chaos. What I want to do on Thursday is talk about this with complex functions, and with complex functions you can make really nice pictures that describe what's happening visually. All right, so there's a little. What we end up with in what we're doing is we end up kind of right on the edge of some really interesting, really complicated, deep mathematics. We end up kind of right on the edge. We don't really get into them, but we end up right on the edge. And I like to talk about what's over the edge a little bit. So chaos is over the edge a little bit from Newton's method. Okay. Anyway, back to the boring old calculations. All right, there we go.